In this video, we will create input-output tables in Desmos to numerically estimate the instantaneous rate of change of a function at a point. The function is given here as f of x equals negative x minus 3 squared plus 5. We're going to use Desmos to estimate the instantaneous rate of change of this function at x equals 4. We're going to do that numerically using tables of average rates of change. We're then going to find the equation of that tangent line and add it to the graph in Desmos. In Desmos, I have defined the function and called it f of x, and we see that it's an open-down parabola. To use average rates of change to estimate the instantaneous rate of change, we're going to create an input-output table that approaches x equals 4 from the left. Then we'll create a separate input-output table that approaches x equals 4 from the right. One way we could do this is by first adding a table, and I'm going to have an input of h, and I'm going to define the average rate of change of the function as the output. So it would be f of 4 plus h minus f of 4 all over h. Within Desmos, you see that the label on the output side of my table, the label for that difference quotient at x equals 4, the label for that average rate of change calculation, you can't see the entire thing. So when you're looking at Desmos, even if you make this wider, it still cuts it off. So it is kind of nice to be able to show your reader the entire label. One way you can do that is to define a new function. I'm going to call it d of x, which is the difference quotient. And I'm going to call that function f of 4 plus x minus f of 4 all over x. And notice what this is really saying is we're going to treat the x in this formula like the h in my difference quotient. I'm going to turn off that graph because we don't need to see that. Then instead of defining that whole average rate of change, that whole difference quotient here, which bleeds off the edge, I could just say that this is d of h now. So now when I plug in h, 0.1, h of 0.01, it is going up to this formula and it's plugging in f of 4 plus h minus f of 4 all over h. This way your reader can glance at it and see what d of x is defined as in your table, and they can see the entire thing. It's not cut off in the label. So now I am exploring the value of this average rate of change. I'm going to turn off the dots here. I'm exploring the average rate of change of f of x at x equals 4. And let me just take the second row of this table and make sure we're clear on what that means. The second row of this table, 0.01, output negative 2.01. That means the average rate of change of f of x from x equals 4 to x equals 4.01 is negative 2.01. The slope of the secant line from x equals 4 to x equals 4.01 is negative 2.01. I'm now going to define a second table. I'm going to use that difference quotient function again, but this time the values of h that I plug in are going to allow me to approach x equals 4 from the left side. So I'm going to let h be negative 0.1, negative 0.01, negative 0.001, and so forth. And we get the average rates of change as we approach x equals 4 from the left. Again, I'm going to uncheck this so that we don't see the points actually plotted. And again, I'm going to interpret the second row of this table. The second row of this table is negative 0.01 and an output of negative 1.99. This is telling us that from x equals 3.99 to x equals 4, The average rate of change of f of x is negative 1.99. The slope of the secant line from x equals 3.99 to x equals 4 is negative 1.99. Now, overall, I'm going to look at these two tables, and I see as the points get closer and closer and closer together as we approach x equals 4, we see the average rate of change of the function gets closer and closer to negative 2. So we can conclude that the instantaneous rate of change of f of x when x equals 4 is negative 2. We can conclude that the slope of the tangent line of f of x at x equals 4 is negative 2. Lastly, we're asked to write the equation of the tangent line at x equals 4 and then graph that on here. T of x for tangent line. The slope of the tangent line is the instantaneous rate of change of f of x when x equals 4, and that instantaneous rate of change we see is negative 2. The slope is negative 2, and we know that it passes through x equals 4, so we plug in x minus 4 plus the y value at that point is 4. The function f of x passes through the point 4, 4. I'm going to change that to a dashed blue line so that we don't confuse it with the actual function f of x. And we see here, I'll also add the point 4, 4, so that it's clear that the tangent line at 4, 4 is given by this equation.